Hi, I'm Declan Knies, and I've been working with Dr. Meenakshi Singh on piezoelectrics in a quantum dot system. So what is a quantum dot? A quantum dot is a group of electrons that is used at a low temperature in order to function as a quantum bit. So what this means is it's a classical style gate, such as a C0 gate, that is just using a quantum bit. So this allows you to perform certain computations faster or more efficiently than a traditional computer can. So what is the problem? Right now, using quantum dots requires extremely low temperatures on the order of decimals of Kelvin, and that is very expensive. It also has high infidelity. What that means is that the noise in the quantum dot system can actually change the accuracy of the quantum dot. It's also very limited in space. Cooling things down to the temperature that quantum dots run is very hard to do, especially exponentially as the space gets larger, which means you're very limited in space, and you're also limited in location. There's only a few places that can actually support such a cold system, and you need a lot of equipment, you need a lot of climate control, and a lot of safety measures in place in order to ensure you can do this. So what is the proposed solution? Now, to reduce noise in the system, which is the main issue for all of those previous problems, we can use piezoelectricity. What is piezoelectricity? That is inducing strain on a system via electricity, or inducing a current on a system via strain. Now we would induce strain via current, and what this can do is it can reduce noise. This can reduce the infidelity, which is the accuracy of the quantum dot. It can reduce the cost, it can reduce the required temperature, and it can also reduce the amount of equipment you need to do this. Now this picture shown is a gallium arsenic wafer, which is actually one of the possible stages that we can use. So it would be what we place the quantum dot on. On top and bottom, there are different strain gauges, which would measure the strain, and the piezo is what actually induces the strain on the system. So what we're doing is we are going to perform an experiment. We are using that previous diagram, except instead of a gallium arsenide wafer, we're going to be using silicon. So what do we need to do? We need to create a quantum dot on a gallium arsenide or silicon wafer. We need to place that wafer in a piezoelectric actuator. We need to place gauges on the wafer to measure resistance, and we need to apply strain to the quantum dot using the actuator. Then we need to measure the resistance to determine the effects on thermal noise. So if this experiment proves useful, we'll be able to raise the temperature at which quantum computers can run. We'll be able to do them with less resources, and we'll actually be able to increase the fidelity of the system, which is overall easier quantum computers.